On the night of August 2nd, 1932, in a darkened laboratory in California, a 26-year-old physicist developed a photograph of something no human being had ever seen. A single hair-thin track of droplets left by a particle from outer space, curving the wrong way. That one wrong-way curve announced an entire hidden half of reality. And here is the astonishing part. 4 years earlier, a mathematical equation had already ordered that particle into existence. This is the story of antimatter, the mirror world. For every kind of particle in your body, there can exist a perfect twin, identical in mass, opposite in charge, and fatal on contact, because when matter meets antimatter, both vanish in a flash of pure energy. It sounds like science fiction. It's in hospitals right now finding tumors, and it was discovered not with a telescope, but with a pencil. Our story begins in Cambridge, England, in the late 1920s, with the strangest and quietest genius in the history of physics. His name was Paul Dirac. He spoke so rarely that his colleagues invented a unit of conversation in his honor. 1 Dirac equals 1 word per hour. He took everything literally, trusted almost no one's intuition, including his own, and believed in one thing above all, mathematics. Dirac had grown up in Bristol under a domineering father who forced him to speak only French at the dinner table. The boy found he could not express himself perfectly in French, so he chose, for much of his life, to say almost nothing at all. What he could not say in words, he learned to say in equations. Mathematics became his native language, and he wrote it with a purity almost no one has matched. The stories about him are legendary. During one lecture, a student raised his hand and said, "Professor Dirac, I don't understand the equation on the blackboard." Dirac said nothing. The silence stretched on until the moderator asked if he would answer the question. Dirac looked genuinely puzzled and replied, "That was not a question, it was a comment. He wasn't being rude, he was being precise." Niels Bohr, the great Danish physicist who mentored a generation, called Dirac the strangest man who ever visited his institute. But inside that strangeness lived something extraordinary, a mind that could follow mathematics anywhere it led, without flinching, without blinking, even when it led somewhere no sane physicist wanted to go. That courage is about to matter enormously. Because in 1927, physics had a beautiful, embarrassing problem. The decade had produced 2 triumphant theories. Quantum mechanics ruled the world of the very small, atoms and electrons. Einstein's special relativity ruled the world of the very fast, anything approaching the speed of light. Each theory worked magnificently in its own kingdom, and they flatly contradicted each other. Schrödinger's famous wave equation, the engine of quantum mechanics, treated time and space in completely different ways, which relativity forbids. It described a slow, lazy electron beautifully. But electrons are not always slow. In atoms, they can move at a serious fraction of the speed of light, where relativity takes over. Any true equation to the electron would have to obey both theories at once. Nobody could find one that worked. Others had tried. An earlier attempt, the Klein-Gordon equation, married the 2 theories but produced nonsense along the way. It predicted, among other things, negative probabilities. A probability is a chance of something happening. A negative chance means nothing at all. The marriage of quantum mechanics and relativity kept producing mathematical monsters, and most physicists quietly moved on to easier problems. Dirac did not move on. Through the autumn and winter of 1927, he worked alone in his spare room at St. John's College, Cambridge, in his usual way. No collaborators, no conversation, playing with the mathematics itself, trying forms of equations the way a locksmith tries keys, listening for the click. He wasn't guided by experiments. He was guided by something he trusted more, mathematical beauty. And in those winter weeks, the lock opened. Dirac found an equation for the electron that obeyed quantum mechanics and special relativity at the same time. Compact, strange, and unlike anything anyone had written before. To make it work, he had to invent a new kind of mathematical object, 4 components deep, that nobody had asked for. He published it in early 1928. Physicists now call it simply the Dirac equation. What happened next was almost eerie. The equation didn't just describe the electron, it knew things about the electron that Dirac had never put in. Electrons spin, behaving like tiny magnets. Experimenters had discovered this, and nobody could explain it. Dirac's equation produced spin automatically, uninvited, with exactly the right strength. It predicted the fine details of hydrogen's light. It was correct in ways its author hadn't intended. Physicists across Europe were stunned. This wasn't a patched-together compromise. It was as if Dirac had found a crack in the universe's source code and read a line of it directly. Today, that one line of symbols is engraved on his memorial stone in Westminster Abbey, a few steps from Isaac Newton's grave. But in 1928, the equation was about to do something far stranger than win admiration. It was about to disobey its own creator, because buried inside the triumph was a scandal. Solve Dirac's equation for an electron, and you get the answers you want, electrons with ordinary positive energy. But you also get, every single time, a second complete set of solutions, electrons with negative energy. Twice as many answers as reality seemed to need. Half the equation described our world. The other half described something else. The trouble comes straight from Einstein. Relativity's full energy law isn't just E equals mc squared, it relates energy to mass and motion. And because that law contains energy squared, taking the square root always yields two answers, one positive, one negative. For every allowed electron, a mirror twin with energy below zero. Now, negative roots usually don't bother anyone. Ask what number squared gives 4, and the answers are 2 and minus 2. But if you're measuring the length of a fence, you throw the minus away without a second thought. It's mathematical debris. Every physicist looking at Dirac's equation expected to do exactly that. Keep the sensible half, discard the negative half, move on. But quantum mechanics has a merciless rule. You can't just ignore solutions. In the quantum world, particles jump between every state that exists. If negative energy states were real, every electron in the universe should tumble down into them. And physics said nothing stopped the fall. Discarding the negative solutions wasn't mathematically honest. Keeping them was physically absurd. Dirac was trapped by his own equation. And the absurdity had teeth. An electron falling into negative energies wouldn't stop. There is no bottom. It would cascade downward forever, radiating an infinite blaze of light on the way. Every atom in existence should have detonated in a flash of gamma rays within a fraction of a second. The equation that explained the electron perfectly also seemed to predict that the universe should not exist. Almost anyone else would have concluded the equation was broken and quietly patched it. Dirac could not. The equation was too beautiful, and it had already been right about too much. So he made a decision that sounds like stubbornness and turned out to be genius. If the mathematics says the solutions exist, then they exist. The question isn't how to get rid of them. The question is, what are they? So hold the problem in your hands, because it's one of the great cliffhangers in science, a perfect equation with twice as many solutions as reality. Negative energy states that can't be thrown away, but would swallow every electron in existence if they're real. For nearly 2 years, Dirac turned it over in that silent mind. And the answer he produced is one of the wildest ideas ever taken seriously. Here it is. In 1930, Dirac proposed that the negative energy states are real and already full. All of them. Everywhere. What we call empty space, the vacuum, is actually a bottomless, invisible ocean of negative energy electrons filling every available state in the universe. Physicists came to call it the Dirac Sea. Nothingness, in Dirac's picture, is the fullest thing there is. Why don't ordinary electrons fall in? Because of a rule called the Pauli exclusion principle, no two electrons can ever occupy the same state. If every seat in the negative energy theater is already taken, there is nowhere to fall. The catastrophe is cancelled. Not because the pit isn't there, but because the pit is packed to the rafters. It sounds insane. But notice, it works. And now comes the move that creates a new world. Ask what happens if you knock one electron out of the sea, give it enough energy to leap up into ordinary existence? It leaves behind a gap, a hole, an empty seat in the infinite theater. And that hole, Dirac realized, would not behave like an absence. To us, watching from above the surface, it would behave like a thing. Think of a bubble in water. The bubble is just missing water. Yet it moves, it rises, it acts for all the world like an object. Dirac's hole is a bubble in the sea of negative charge, and the mathematics said it would look exactly like a particle, with the same mass as the electron, but the opposite electric charge. Positive. A mirror image electron made of pure absence. At first, Dirac flinched. In 1930, physics knew exactly two particles, the electron and the proton. Inventing a third seemed extravagant, almost improper, so he suggested the whole might simply be the proton, the only positive particle anyone had ever seen. It was the cautious choice, the economical choice. It was also, as his colleagues quickly showed, impossible. The mathematician Hermann Weyl proved the whole must have exactly the electron's mass, and the proton is nearly 2,000 times heavier. Robert Oppenheimer added a lethal blow. If holes were protons, every hydrogen atom in the universe would devour itself almost instantly, electron and proton annihilating in a flash. The escape route was closed. The mathematics would accept no known particle. So in May 1931, Paul Dirac wrote one of the most quietly audacious sentences in the history of science. The whole, he stated, would be a new kind of particle, unknown to experimental physics, having the same mass and opposite charge to an electron. We may call such a particle an anti-electron. No hedging. A brand new inhabitant of reality, specified in advance, mass, charge, and behavior, entirely from mathematics. Stop and feel how strange that moment is. Nobody had seen this particle. No experiment demanded it, no telescope, no lab bench, no photograph. Just a silent man in Cambridge saying, "My equation has twice as many solutions as your world, so your world is only half of what exists. Somewhere there must be electrons of antimatter. It should be there. Go and look." The reaction was brutal. Wolfgang Pauli, the sharpest tongue in physics, scoffed at the whole hole theory. Werner Heisenberg privately called it the saddest chapter of modern physics. Even Dirac's admirers winced. The same 1931 paper casually proposed magnetic monopoles too, and it all felt like beautiful mathematics losing contact with reality. The anti-electron was, most agreed, an elegant embarrassment. But Dirac had a compass the others didn't fully trust. He believed the universe is built on beautiful mathematics, that a sufficiently beautiful equation is more likely to be true than an ugly one that merely fits today's data. It is a dangerous way to do science. It fails far more often than it works. And once in a century, it hands you a continent no ship has reached. So there the prediction sat, printed, precise, and unclaimed. A wanted poster pinned to the wall of physics. Same mass as the electron, opposite charge. No one had the faintest idea how you would ever catch such a thing or where you would even look. The answer, it turned out, was already falling out of the sky. Because our planet is under constant bombardment. Every second, particles from deep space, launched by exploding stars and forces still half understood, slam into the atmosphere at nearly the speed of light. In 1912, the Austrian physicist Victor Hess had ridden hot air balloons to dangerous altitudes and proved this radiation comes from above, not from the ground. The sky, it turned out, is raining pieces of the universe. In California, the formidable Robert Millikan, Nobel laureate, scientific empire builder, named them cosmic rays and made them Caltech's obsession. What were they? What were they made of? To find out, he handed the problem to a young graduate student with gifted hands and boundless patience, Carl Anderson, the son of Swedish immigrants still in his mid-20s. Anderson knew nothing of Dirac's mirror world. He was an experimenter chasing cosmic rays, not a theorist chasing beauty. Which is exactly what makes what happens next so perfect. Two people, an ocean apart, one armed with an equation, one with a camera, about to collide on the same hidden truth. Now cross an ocean, and cross from silence to noise. At the California Institute of Technology, Robert Millikan had built one of the most powerful pieces of scientific hardware on Earth, a cloud chamber wrapped inside an enormous electromagnet, its coils drawing enough current to dim the lights of Pasadena, all built to answer one question: what, exactly, falls out of the sky? Here's how it worked. A charged particle streaks through the chamber, leaving a trail of condensed droplets, a fog trail, like a jet's contrail, and the magnetic field bends that trail into a curve. Curve tightly, and the particle is slow or heavy. Curve gently, and it's fast or light. Curve one way, and it's negative. Curve the other, and it's positive. The photograph does the physics for you. But there was a catch, a genuine ambiguity nobody could wave away. A single curved track cannot tell you which direction the particle traveled. A positive particle moving up curves exactly the same as a negative particle moving down. Without knowing direction, you cannot know the sign of the charge. Anderson needed a way to force the particle to reveal, unmistakably, which way it had come from. His solution was elegantly brutal. Anderson bolted a 6mm slab of lead straight across the middle of the chamber. Any particle crossing it would be forced to shed energy, slow down, and curve more sharply on the far side. Compare the bend above the plate to the bend below it, and the direction of travel, and therefore the sign of the charge, could no longer hide. On the evening of August 2nd, 1932, sorting through the day's photographic plates in his darkroom, Anderson found one image unlike the thousands before it. A single thin, faint track entered from below the lead plate, crossed it, and curved noticeably tighter above. Whatever left that trail had slowed down crossing the lead, meaning it had traveled upward, out of the Earth, not down into it. Combine that direction with the way the track curved in the known magnetic field, and the arithmetic was unavoidable. The particle carried a positive charge. But its track was thin and faint, far too lightly traced for a proton, which would have barely bent at all and left a thick, heavy scar. This particle bent like an electron. It was simply wearing the wrong sign. Anderson measured it properly. The particle entered at about 63 million electron volts of energy, lost roughly 40 million crossing the lead, and left with about 23 million, a huge, violent slowdown that only a wisp-light particle could undergo and survive. The mass came out within the noise of the electrons. A positive particle, electron light. Nothing like it belonged on any known chart of matter. Here is the twist that makes this story so delicious. Anderson was not hunting Dirac's anti-electron. He barely knew the theory existed. He was simply a careful young experimenter cataloging whatever cosmic rays threw at him. And cosmic rays had just thrown him something that, unbeknownst to him, a Cambridge equation had already ordered into existence 4 years earlier. Decades later, Anderson admitted it outright. The discovery of the positron was wholly accidental. He even said, with startling honesty, that any physicist who'd simply taken Dirac's theory at face value could have found the particle in a single afternoon of looking. Instead, it took a fog chamber, a slab of lead, and sheer observational discipline, theory and evidence arriving by two entirely different roads. Cautious by nature, Anderson didn't announce a new fundamental particle with fanfare. In September 1932, he published a short, careful note in the journal Science, titled, almost shyly, The Apparent Existence of Easily Deflectable Positives. No grand claims yet, just data, precisely reported, and a request that the world take a careful second look. When Anderson wrote up the fuller paper for Physical Review in 1933, titled simply The Positive Electron, the journal's editor suggested a snappier name for the new particle, a fusion of positive and electron, the positron. Anderson adopted it. The word the whole world now uses for antimatter's first member wasn't even his own coinage. Skeptics were not satisfied by one photograph. A single ambiguous track could be a coincidence. A misidentified proton, a chamber artifact, a fluke of chance. Extraordinary claims, a whole new species of matter, demanded independent eyes, independent chambers, independent proof, on the other side of an ocean, before the physics world would fully believe it. That proof came fast. In Cambridge, Patrick Blackett and Giuseppe Occhialini had built something cleverer, a cloud chamber wired to Geiger counters, so it photographed itself automatically. The instant a cosmic ray actually passed through. No wasted film, no guesswork. By early 1933, they had dozens of clean, unambiguous tracks. The positron was real, repeatedly on demand. And Blackett and Occhialini went further than confirmation. They saw whole showers of tracks, positive and negative particles appearing together in matched pairs, and they explicitly framed what they were seeing through Dirac's whole theory. The mathematics from the silent man in Cambridge and the photographs from his own university's laboratory had, at last, met face to face. What they'd caught a name for was pair production. A gamma ray passing close to an atomic nucleus can convert itself entirely into two particles, one electron, one positron, matter and antimatter, minted together from a single burst of pure light. Energy becoming mass, exactly as Einstein's equation allows, running for once in the direction nobody expects. And the process runs backward too, more violently than it runs forward. Bring an electron and a positron together, and they do not collide like billiard balls, they annihilate. Every scrap of both particles' mass converts, instantly and completely, into two gamma-ray photons of exactly 511,000 electron volts each, flying off back to back. Meeting your mirror twin is fatal to you both. Word of it all reached Cambridge, and reached Dirac himself. For 2 years, his anti-electron had been physics' embarrassing joke, an elegant indulgence, Pauli's sneer, Heisenberg's saddest chapter. Now a photograph from a mountain laboratory in California said, in the plainest language photons can speak, that the silent man's mathematics had been describing something that was really out there. Measure the distance traveled. Dirac's prediction was printed in May 1931. Anderson's photograph was developed in August 1932, 15 months later. Blackett and Occhialini's confirmation followed within another 7. A little over 2 years carried an idea from pure, unloved mathematics to repeated, undeniable proof, one of the shortest journeys from pencil to photograph in the history of physics. Two men, an ocean apart, had never spoken, never collaborated, barely knew of one another's work, and together they had doubled the known contents of the universe. One had reasoned his way there with nothing but algebra and nerve. The other had stumbled onto it with a camera, a magnet, and the patience to look twice. Both were about to be recognized for it. In 1933, the Nobel Prize in Physics went jointly to Erwin Schrödinger and Paul Dirac for the discovery of new productive forms of atomic theory. Notice what the citation does not say. It never mentions antimatter by name. It honors the equation itself, the marriage of quantum mechanics and relativity, as if the anti-electron were simply one more consequence, almost an afterthought, of a deeper triumph. Dirac, true to form, seriously considered refusing the prize, not out of false modesty, but because he dreaded the publicity a Nobel would bring to a man who valued silence above almost everything. It was Ernest Rutherford who talked him out of it. With blunt, wonderful logic, refusing, Rutherford said, would only get him more publicity, not less. Dirac reluctantly accepted. At 31, Dirac became one of the youngest Nobel physics laureates in history, forced into a whirl of banquets, speeches, and photographs he plainly hated. Colleagues told stories for years afterward about the world's most famous silent man, trapped for a week inside the very spotlight he had spent his entire life quietly avoiding. 3 years later, in 1936, it was Carl Anderson's turn. He shared the Nobel Prize in Physics with Victor Hess, the very man whose 1912 balloon flights had first proven cosmic rays existed at all. Anderson's citation was refreshingly direct, awarded simply for his discovery of the positron. The camera had caught up with the pencil. There's a pleasing symmetry in it. The theorist won for an equation nobody could fault, but everyone doubted. The experimentalist won for a photograph nobody could fault, and everyone had to believe. Between 1933 and 1936, in the space of 3 short years, physics had formally honored both halves of the same discovery, the mathematics and the proof. And the loose threads finally tied off for good. Weyll's proof that the whole had to share the electron's mass, Oppenheimer's warning that a proton hole would let every hydrogen atom devour itself instantly, every objection that had once trapped Dirac's theory now simply confirmed it. The impossible particle had turned every argument against it into a description of exactly what it was. But the deepest implication was still ahead. If the electron had a perfect mirror twin, logic demanded the question, did every particle have one? Not just the electron, the proton too. Perhaps every single building block of matter came paired with an opposite waiting to be found if anyone could build a machine powerful enough to make one. It took until 1955. At Berkeley, physicists Emilio Segre and Owen Chamberlain built the Bevatron, a particle accelerator engineered specifically with enough energy to manufacture the proton's antiparticle on demand. That August, they found it, the antiproton, same mass as a proton, opposite charge, exactly as symmetry required. Dirac's idea wasn't a quirk of the electron, it was a law of nature. Segre and Chamberlain won their own Nobel Prize in 1959, and the mirror world kept growing, an antiproton, an antineutron, and, by the logic of the whole idea, the possibility of entire antiatoms. Physicists began to wonder whether, somewhere in a universe this vast, there might exist whole worlds built from nothing but antimatter. In 1995, at CERN in Switzerland, physicists manufactured the first complete anti-atoms ever made, 9 fleeting atoms of antihydrogen, an antiproton paired with a positron existing for a few billionths of a second before annihilating. It was the strangest possible confirmation of Dirac's silent equation, an entire mirror atom built to order in a laboratory. But antimatter's most useful legacy isn't in a particle accelerator. It's in a hospital, a PET scanner, positron emission tomography, injects a patient with a mildly radioactive tracer that emits positrons as it decays inside the body, tracking exactly where cells are working hardest, a beating heart, an active brain, a hungry tumor. Each emitted positron travels barely a millimeter before finding an ordinary electron and annihilating, producing that same signature pair of 511 keV gamma rays, flying off in exactly opposite directions. Detectors ringing the patient catch both photons at once and draw a line straight back to where the annihilation happened, mapping disease with pinpoint precision. Every single day, millions of people are scanned by a phenomenon. A socially awkward Cambridge theorist worked out with nothing but pencil and paper 90-some years ago in a room where he spoke to almost no one. Antimatter isn't science fiction. It's a Tuesday morning at your local hospital. It's also, gram for gram, the most expensive substance human beings have ever produced. NASA once estimated a gram of antihydrogen would cost on the order of $62 trillion to manufacture. At the rate the world currently makes antiprotons, assembling a full gram would take far, far longer than the present age of the universe. Which brings us to the strangest, least resolved part of this entire story. If matter and antimatter are true mirror twins, created together, destroying each other on contact, then the Big Bang, which had unimaginable energy to spend, should have produced them in exactly equal amounts. And equal amounts of matter and antimatter should have annihilated each other completely, leaving behind nothing but light. But the universe is not empty. You are proof of that. Somehow, for every roughly billion matter-antimatter pairs that existed in the universe's first instance, about 1 extra matter particle survived with no antimatter partner to destroy it. That tiny, unexplained surplus, 1 part in a billion, is the entirety of everything. Every star, every planet, every person who has ever lived. Why matter won that lopsided contest is one of the biggest open questions in all of physics, called baryogenesis, and it isn't solved. Physicists know some of the ingredients required, laid out by Andrei Sakharov in 1967, and they're hunting for tiny asymmetries in how matter and antimatter particles decay at labs from CERN to Japan right now. Trace the thread all the way back, and it runs through the same silent equation. The physics that hands a doctor a picture of your beating heart is the same physics that, applied to the birth of everything, produces one of the deepest unanswered questions a human being can ask. Why does the universe contain anything at all? Dirac himself lived on quietly for decades, eventually settling at Florida State University, still famously saying almost nothing, still trusted by physicists as the deepest thinker most of them had ever met. He died in 1984, having spent a lifetime insisting, through silence and through equations, that beauty was the surest guide to truth. Carl Anderson, for his part, kept hunting cosmic rays at Caltech, and in 1936, the very same year as his Nobel Prize, he and his student Seth Nettermeyer found a second entirely new particle in their chamber, the muon, a heavier, unstable cousin of the electron. One young experimenter's careful eye doubling the universe's inventory twice over. Niels Bohr called Dirac the strangest man he had ever met at his Copenhagen Institute, and meant it with real affection. What Bohr had recognized was a mind willing to follow an equation into territory that felt, to everyone else, like nonsense, and to trust it there long after the room had stopped believing him. Stop and hold the shape of the whole thing. An equation built from pure aesthetic instinct in a cold Cambridge room insisted a second half of reality existed, one nobody had asked for, one that embarrassed its own creator for 2 full years. And it turned out to be sitting in the sky the entire time, raining down as cosmic rays. Lay the whole arc out, start to finish, and it reads like the tightest plot in the history of science. An equation in 1928, an audacious prediction in 1931, a photograph in 1932, independent proof and 2 Nobel Prizes soon after, and, decades later, hospitals and an unanswered cosmic mystery, both still running on the very same idea. So, what does this story leave us with? First, and most startling, mathematics, done honestly and followed without flinching, can outrun experiment entirely. Dirac never went looking for a new particle. He went looking for an equation that didn't contradict itself, and the universe handed him antimatter as a side effect of asking for consistency. Second, courage matters as much as cleverness. Plenty of physicists saw the same negative energy solutions Dirac saw. Almost all of them threw the negative half away as mathematical debris, the way you'd discard a negative answer to a fence measuring problem. Dirac alone insisted that if the mathematics said it existed, and he was right. Third, remember how ugly the middle chapter was. For 2 years, Dirac's idea was mocked as an elegant embarrassment. Pauli scoffed. Heisenberg called it physics' saddest chapter. Being right in science is often lonely long before it is celebrated, and the sneering of respected colleagues is not, in itself, evidence that you are wrong. Fourth, Anderson's half of the story teaches the opposite lesson just as powerfully. You don't need to be chasing a theory to stumble into truth. Careful observation, done with discipline and without an agenda, can find the exact same reality a theorist reasons his way toward arriving by a completely different road and arriving just as validly. And when theory and blind observation converge on the identical answer from 2 people who never spoke, on 2 continents, using entirely different tools, that convergence is one of the strongest kinds of proof science ever produces. Not because either method alone was certain, but because 2 unrelated paths landed on the very same place. Fifth, the deep unresolved gift this story leaves us with. We still do not know why matter beat antimatter in the earliest instant of the universe. That mystery isn't a footnote. It is the reason there is a you to read these words instead of an expanding, empty fog of light. Your existence rides on a cosmic coin flip nobody has explained. Think about that seriously for a moment. Every atom in your body is part of the roughly 1 in a billion surplus that escaped total annihilation in the universe's first fraction of a second. You are, quite literally, leftover matter. The residue of a near-total mutual destruction that, for reasons no one yet understands, wasn't quite total. Dirac summed up his whole approach to physics in one sentence decades later. It is more important to have beauty in one's equations than to have them fit experiment. It sounds almost reckless, but antimatter is the proof that, at least once, trusting beauty over immediate confirmation uncovered something experiment hadn't even known to look for. It's worth marveling at the sheer range of consequence packed into one silent man's idea. The same theory that lets doctors see a tumor light up on a screen this afternoon is the theory forcing physicists this same afternoon to hunt for why the entire universe exists at all. Few equations in history have stretched that far, in both directions at once. Picture holding actual antimatter in your hand. You couldn't, of course. It would annihilate on contact with the container itself, let alone your skin. Every particle of it humanity has ever made would fit, all together, in a container smaller than a grain of rice and could vanish in a flash brighter than you'd want to stand near. Go back to where we started. A single, hair-thin track curving the wrong way in a darkened California laboratory. That one photograph announced an entire hidden half of reality. A half that had been raining down from space for the whole of human history, unnoticed, until one careful young man looked closely enough to see it curve backward. Honor them both equally. Paul Dirac, who trusted an equation into the strangest corner of mathematics anyone had dared explore and never once needed applause for it, and Carl Anderson, who trusted his own eyes over any theory and found the same truth waiting in the sky. A pencil and a camera discovering the same universe. This same pattern, pure mathematics naming something before any instrument had seen it, echoes across the history of physics, from Neptune's orbit predicted before it was glimpsed, to particles theorists describe today that experimentalists spend decades hunting down. Antimatter remains one of the cleanest, fastest examples ever recorded, prediction to proof in about 2 years. Antimatter research hasn't stopped being useful for asking fundamental questions either. At CERN today, the ALPHA experiment traps antihydrogen atoms in midair with magnetic fields and studies them in exquisite detail, testing, among other things, whether antimatter falls under gravity exactly the way ordinary matter does, or whether the mirror has some final subtle crack in it. Remember the boy forced to speak only French at his father's dinner table, who found he couldn't express himself, and so, mostly, stopped trying, and instead built his entire inner life out of mathematics instead of words. That imposed silence became the sharpest tool in 20th century physics. Sometimes the strangest constraints shape the most extraordinary minds. And remember, too, that Anderson almost dismissed his own photograph. A single strange track could easily have been filed away as an oddity, a chamber contaminant, a mistake not worth chasing. Great discoveries often look, at first glance, exactly like errors. And the only difference between an anomaly and a revolution is whether someone trusts it enough to look twice. The bigger idea beneath all of this is called CPT symmetry, the deep suspicion built into the very structure of physics that every particle has a mirror opposite, and that the laws of nature themselves look the same if you flip charge, mirror space, and reverse time altogether. Dirac's spare room equation was our first real glimpse of that symmetry. So the hunt continues. Physicists keep making antimatter, gram by unimaginable fraction of a gram, testing whether its gravity, its spectrum, its every last property truly mirrors ordinary matter. Because if they ever found one crack, one asymmetry, it might finally explain why the universe is here to test it in the first place. From a silent man's equation, to a photograph in a dark room, to 2 Nobel Prizes, to a PET scanner reading your own heartbeat, to a question that still humbles the smartest people alive: why does anything exist at all? That is the entire arc of antimatter, and we are, every one of us, living proof of its answer, whatever that answer turns out to be. Stay curious about the impossible solutions you're tempted to throw away, in an equation, in an argument, in your own thinking. Sometimes the ugly, embarrassing, inconvenient answer isn't a mistake to be discarded. Sometimes it's a whole undiscovered half of reality, patiently waiting for someone stubborn enough to take it seriously. And stay curious about the mirror in everything, because the same instinct that found antimatter in an electron's equation keeps finding hidden symmetries throughout nature, again and again. The next embarrassing, unwanted solution some quiet theorist refuses to throw away might be waiting right now to double the universe again. If this story stuck with you, do 2 quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just 1 click away. I'll see you there.